When astronomers gaze into the heavens, they often expect predictability. Stars rise, planets orbit, and comets follow their icy dances around the sun, shaped by forces we understand with near clockwork precision. Yet every once in a while, the universe disrupts our sense of order with something so unusual, so alien, that even the most experienced researchers are forced to pause and reconsider their models. In July 2025, such a moment arrived with the discovery of 3I Atlas, the third confirmed interstellar object to enter our solar system. This was no ordinary comet. Early observations suggested a body far larger and heavier than the ones that preceded it. Oumuamua in 2017 and 2I Borisov in 2019, where those two were, either fleeting and mysterious or relatively ordinary, 3I Atlas seemed determined to break the mold. Detected by the Atlas survey in Chile, its hyperbolic path immediately confirmed it as an outsider, an emissary, from beyond the sun's gravitational domain. That alone would have made headlines, but what followed was even more extraordinary. The comet's nucleus, estimated to be nearly 5.6 kilometers across, placed it firmly in the category of massive comets, but its physical behavior defied expectations. Unlike most comets that respond noticeably to the push of outgassing, jets of gas and dust acting like tiny rocket engines, 3I Atlas barely flinched. Despite a visibly active coma and significant outgassing, its trajectory showed only minuscule deviations from gravity's pull. For astrophysicists, this was puzzling. The implication was that the nucleus possessed immense mass, tens of billions of tons, making it one of the heaviest interstellar travelers ever recorded. And weight is only part of its anomaly. Spectral readings revealed an unusually high concentration of carbon dioxide compared to water, placing its chemistry at the extreme end of what comets typically display. Ultraviolet data hinted at water vapor persisting even at distances where comets usually remain dormant, suggesting that 3I Atlas carries volatile reserves capable of activating far from the sun's warmth. To add to the intrigue, polarization studies show dust, properties that didn't quite match any known comet or asteroid population, perhaps hinting at an origin environment vastly different from our solar nursery. Some astronomers even whispered about early signs of nickel appearing without the usual iron signature, something virtually unheard of in natural cosmic chemistry. Whether that detail holds or fades under further scrutiny, it adds another layer to the comet's growing list of peculiarities. This is not simply another frozen rock drifting through our neighborhood. It is a heavyweight, interstellar traveler that challenges the assumptions we have long relied upon, raising uncomfortable but exciting questions about what else might be wandering between the stars. The real fascination with 3I Atlas is not just in its size or its path, but in what those details reveal about the broader puzzle of interstellar objects. Think of comets as nature's messengers, tiny archives carrying chemical signatures from the places they were born. When such an object enters our solar system, it is as though a piece of another star's history has been dropped at our doorstep. With 3I Atlas, that history is unusually heavy and unusually strange. Astronomers worldwide rush to record every motion of the object, gathering astrometry from more than 200 observatories across the globe. They found that despite the visible outgassing, the comet was remarkably resistant to deviation from its gravitational trajectory. The push from jets of sublimating gas, which should have nudged it noticeably, barely left a mark. The conclusion was inescapable. The nucleus of this comet is far denser and more massive than anyone anticipated. To put it in perspective, if 3I Atlas really carries a mass of tens of billions of tons, then we are dealing with something that rivals some of the largest solar system comets, but with the added twist of being a traveler from another star system entirely. And that introduces a major tension in our understanding of how interstellar debris should be distributed. Conventional models tell us that interstellar wanderers should mostly be tiny, pebble-sized, or at best small boulders, since those are the fragments most easily ejected during the chaotic youth of planetary systems. Larger bodies, kilometer-sized and active like 3I Atlas, should be vanishingly rare. Yet, instead of a parade of small objects, our first three confirmed visitors, Oumuamua, Borisov, and now Atlas, are all big enough to detect and track in detail. That either means our surveys have been blind to a much larger population of small interstellar objects, or the galaxy does not follow the neat distribution we assumed. Both options carry weighty implications. If we've been missing the smaller ones, Then improved surveys like the upcoming Vera Rubin observatory may suddenly uncover a flood of faint hyperbolic objects, rewriting our statistical models overnight. But if nature genuinely favors larger, heavier bodies, then our theories of planetary system formation will have to be re-examined. Perhaps young systems eject more massive cores than predicted, or perhaps processes we have yet to understand are at work, shaping how material escapes into interstellar space. Whatever the truth, 3I Atlas has effectively forced astrophysics into a corner. The rules may not be what we thought they were, and that, for scientists, is both unsettling and exhilarating. It means the universe has surprises left, and that our telescopes are just beginning to catch them. If mass and motion set 3I Atlas apart, its chemistry raises even sharper questions. Spectroscopic studies quickly revealed that this comet's coma is unusually dominated by carbon dioxide, with CO2 levels exceeding those of water, a stark reversal of what we typically see in comets native to our solar system. Normally, water ice is the star of the show, driving activity as sunlight warms the nucleus. Here, however, CO2 is taking center stage, suggesting that Atlas formed in a region of its home system where carbon dioxide was abundant and stable. This already paints a picture of an environment very different from the one where our local comets were born. But the surprises did not end there. Ultraviolet detections of water vapor appeared at unexpectedly large distances from the sun, hinting that this comet can activate far earlier than most, releasing gases at ranges where ordinary comets remain frozen and silent. That suggests a composition unusually rich in volatile ices, or perhaps a structure that allows heat to penetrate deeper than normal. Add to that the strange polarization patterns in the dust, which imply grains scattering sunlight in ways inconsistent with standard cometary or asteroid populations, and we are faced with the possibility that Atlas is not just chemically unusual, but physically different down to the structure of its dust. Then came perhaps the most puzzling clue of all: tentative signals of nickel without iron. In cosmochemistry, nickel and iron are siblings. They form together in stellar furnaces, travel together in meteorites, and are almost always found side by side in planetary material. To detect nickel without iron is like hearing half a duet, where the other voice is missing. It could be a calibration artifact, an error born of complex data reduction. But if real, it would represent a truly exotic fingerprint, one that does not match the playbook of solar system chemistry. It is no wonder, then, that the scientific community is divided in its interpretations. On one side are voices like Avi Loeb, who argue that if these anomalies persist under scrutiny, then conventional natural models may not be sufficient, and we must at least be open to unconventional explanations. On the other are mainstream comet scientists, including NASA's Tom Statler, who emphasize that despite the oddities, 3I Atlas still behaves in most respects like a comet, active jets, a coma, a tail, just a larger and more extreme specimen than we have seen before. This tension is vital. It ensures that speculation remains tethered to evidence, that instruments remain pointed, and that the truth, however strange or ordinary, is decided by data. For now, Atlas stands as a living laboratory, an object that refuses to be boxed neatly into existing categories. Its chemistry, far from being a footnote, is the loudest part of its story, a challenge hurled directly at our models of how comets form, evolve, and migrate across the galaxy. As 3I Atlas continues its one-way journey through our solar system, the urgency of observation cannot be overstated. Unlike periodic comets that return on predictable paths, this interstellar traveler will never circle back. Once it swings past the inner planets, it is gone forever, carrying its secrets back into the galactic dark. That fleeting nature has united the global scientific community in a rare, coordinated campaign. Dozens of observatories, spacecraft, and space agencies are working in tandem, each probing the comet from a different angle. The Mars flyby on October 3, 2025, gave researchers a front-row seat. From orbit, instruments like HiRISE, MAVEN, and the Trace Gas Orbiter captured data Earth could never resolve, helping constrain dust grain sizes, coma structure, and even the geometry of its jets. At nearly the same time, Atlas was struck by a coronal mass ejection from the Sun, a plasma storm that had the potential to shear its tail away, just as solar storms have done to other comets in the past. For scientists, this was not a threat, but a gift, a natural experiment, testing how interstellar dust and plasma interact under extreme conditions. These snapshots, Mars imaging, CME disruption, ultraviolet detections, polarization curves together build a composite portrait of an object that challenges every neat category we thought we understood, and the story is far from over. By December 2025, Atlas will re-emerge from behind the sun brighter than before, its coma swollen by weeks of solar heating, its tail stretched and sculpted into new forms. This reappearance will be the moment for the Vera C. Rubin Observatory to flex its unprecedented wide-field power, catching deep nightly images that track every flicker of variability. Meanwhile, the James Webb Space Telescope and other infrared observatories will dissect its spectrum, molecule by molecule, searching for isotopes that whisper of its birthplace in some distant, alien star system. The stakes are profound. If Rubin finds that Atlas is an outlier, an oversized exception, among mostly smaller, faint interstellar comets, then it becomes a curiosity, a giant dice roll from the universe. But if other massive interstellar visitors appear with surprising frequency, then the implications ripple across planetary science. Young solar systems may be ejecting heavyweight planetesimals far, more often than we thought, seeding the galaxy with material that could jumpstart the growth of planets elsewhere. Either way, Atlas serves as a stress test, a probe of whether our models can stretch to match reality or whether they must be rewritten. For the public, it may be remembered as a headline about a mysterious visitor from the stars. For astronomers, it will be a milestone, proof that the sky is not a static museum but a living laboratory, where every unexpected anomaly is an invitation to learn. Atlas is not just a comet, it is a cosmic experiment in motion. And its lesson is clear: the universe will not fit neatly into our predictions, but it will reward those who dare to look closely before the moment slips away.